Hello, everyone. All right, we got the screen working. We're going to go ahead and get started. All right, thank you all for joining us. Before we get started, I did want to say, on behalf of T-Mobile, we are so happy to have had the amazing opportunity to sponsor such a great event like this. It's been great. Please take the time to check out one of our booths we got up here. We got a little lounge area down there. We got some raffles outside. So please interact with us. We'd love to talk to you about cybersecurity and any other questions you may have. But for the next little bit, what we wanted to do is kind of continue along with some of these amazing discussions that have been happening so far and give you all a little insight into a cybersecurity risk that is ever present, ever growing, which is the risks of using dependencies. A little bit about me. I currently, obviously, work at T-Mobile. I'm on the offensive security team. We're responsible for running the pen test program, bug bounty program, threat emulation, anything that kind of falls in the red team bucket. That's where we are, and that's what we're touching. Prior to that, I worked for 2 years in an application security role in the finance industry. And so this talk has been an amazing opportunity to kind of meld those two different areas of background into understanding how everything is used. And someone who's not able to join us today, an application engineer by the name of Schwarte, has been an amazing resource in building out this application, understanding from the developer's standpoint how these dependencies are being utilized on a day-to-day basis, which is essential for us as security to understand if we really want to have any kind of impact in securing how they're being used. So before we kind of dive into the technical details, I want to make sure that we all have a baseline understanding of some of the terminology I'm going to be using. When I say dependency, the kind of technical definition is a relationship between the software components. One component relies on the other to work properly. All this means is when you're writing a piece of code and you have a single file, if your code relies on external code that is not in the file itself, whether it's you wrote it, whether you downloaded it from the internet, whatever it is, your code is dependent upon it. It is a dependency of your code. And depending on the different programming language or structure that you're using, there's different kind of terminology that's utilized to explain the different types of dependencies as how they're structured in code. The most basic is going to be your component. That's a single file that's being utilized. Technical example, primary button.js, that specific file is an individual component. If we're using analogies, think of it like a big bucket of Halloween candy. Any of those individually wrapped pieces of candy, your lollipops, your Tootsie Rolls, a single piece of candy individually wrapped, that's a component. Moving to the next step, we've got a package. It's going to be a collection of components all stored in a directory. So with that analogy, think of like your Skittles, your M&Ms, in multiple different pieces of candy, all for a single serving wrapped in one package. And our technical definition, Fluent UI, in which you have the primary button component. And finally, a library, that's your giant bucket of candy. That's a collection of different components, packages, all wrapped together for a single function. And in our explanation here, we have React. And so when you're using this in your code, it's going to look something along the lines of import the component primary button from the Fluent UI package within the React library. That's kind of how you would be utilizing it in an actual code sentence. And then finally, there's different ways in which we understand the source of these different dependencies and where they're coming from. Likely you're familiar with some of this terminology. Open source, it's publicly available software or code anybody can use, modify, and share. Essentially what we're looking at, it is untrusted code coming from a source that you don't maintain. Regardless of your personal opinions on whoever is developing and maintaining the code, you, from a trust perspective, cannot ensure that it is coming from a trustworthy source, and you yourself are not maintaining it. Third party, typically something along the lines of vendors, is code that is technically trusted because you will have a contract in place. Again, regardless of your individual feelings about whether or not you trust a vendor, it is technically trusted code because you have those protections in place from a legal standpoint. And finally, internal is trusted code that you do maintain because you're building it in-house. And lastly, a package manager is an actual tool that's automating the installation, the updating, and managing of all these different dependencies. The idea being when you have a whole lot of different ones, you need a place in order to store them, to maintain them, to gather them. And this is where that's going to be. It's going to vary based on the actual programming language that you're using, whether it's an internal or external resource. For example, Python is going to be using PyPy. NPM is the Node.js library. But why do we care about this? Why are we talking? So some of you may have seen this image before. It's a representation of the modern digital infrastructure in which we have a lot of different reliances, a lot of important stuff. That all the way at the bottom, there's a dependency that is being utilized from an open source contributor, someone who is not actually is not someone that we can technically trust, right? We're not employing them, we don't have any legal interactions. So there is the ability for, if that is to fall, if that person decides to not maintain that code, if there's a vulnerability, everything else can topple. And if we're looking at some actual statistics, Black Duck just last year did a research auditing several hundred different code repositories and identified that 97% of these code bases contain some form of an open source dependency, which is an increase 3 times more dependencies that are being utilized in the past 4 years. The most common package manager that we're seeing these resources coming from is NPM. And in these code bases that were studied, 86% of them have some form of vulnerability as a direct relation of their open source dependencies. So it's just kind of shocking the amount of reliance that we have on these open source dependencies and sometimes the minimal security risks that we have in relation to ingesting them. So now, what are some of the security threats that we actually care about in relation to these dependencies? Supply chain attacks. Now, technical term, type of cyber attack that targets a third-party offering, service, or software vital to the supply chain. Essentially, any time in which an individual piece of software, technology, resource is being compromised prior to the actual end target victim, you're compromising the software or the supply chain that then becomes a supply chain attack from the cybersecurity standpoint. There's many, many different types of supply chain attacks. I've loosely grouped them into 4 different buckets here. There's some real life examples if you want to take a look. Unfortunately, we don't have enough time to kind of dive deep into each one of these, but the 4 kind of groups that we have here is a hardware attack. Think an actual physical piece of hardware that's coming off of a factory line gets compromised in some way prior to reaching the actual customer, which then allows for backdoors or other pivoting access into a company organization from the hardware itself. CI/CD pipeline, similar, except we're looking at the actual CI/CD pipeline or their software development lifecycle toolings and resources in which those are being compromised, typically exfiltrating information of internal secrets or information about different code bases, all of which can be utilized nefariously for malicious intent. Upstream attack is the kind of more stereotypical supply chain attack that people will think about when we talk about cyber supply chain attacks, in which you have an end target, typically a company that maybe has more security controls in place and is harder to go directly attack. So instead, you look at their vendors, their third parties, other clients, or people who have access to their network. You target them, which by proxy allows you to gain access to your end target. And finally, dependency attack, which we'll be talking about for the remainder of this talk, in which you have most commonly an open source dependency that is compromised, whether it is the maintainer decides to all of a sudden apply some malicious code, they're compromised and their account's taken over, someone adds something that isn't maintained, and their code, untrusted code, is implemented into your environment that is then able to be running malware or whatever the intent of the attack is. So I want to kind of give a breakdown of the supply chain attack, how it's actually working, and first off, to kind of demonstrate what it looks like in terms of how people are utilizing dependencies currently, right? So from a developer's perspective, what does this kind of flow look like when someone needs a dependency installed in their software? So here we have a developer. They're going to be working inside our company intranet. They're inside the network. We're not exposed to the internet at all. They're going to want to create some application. In this case, it's pre-production. It's still on our network. And that application is going to require a dependency. In order to get the dependency, the application is going to reach out to the package manager. Depending on how the company structures their network, this may live inside the network, it may live outside. For purposes here, we'll say it lives right on the edge of our network. This package manager is then going to go call the dependency that is required, bring it back into the network, and use it in the application. At this point, whatever untrusted code is out there, be it for good intention, bad intention, it is inside our environment and has the ability to be executed and be used inside the environment without any restrictions, depending on the security mechanisms we have in place. Then the application is going to be protection, whether or not this is used for internal, external, doesn't matter, has the potential for clients to be utilizing it, and now we have this code running on an end application. The thought process here then is this dependency, what happens when you have an attacker that is the one who's initially creating it and deploying it. So in this case, looking at it maliciously from the kind of the attack kill chain, we're looking at an attacker publishing a malicious open source component, ideally something that either has a high usage, is very popular or is advertised as being something that an internal employee may want to use for their own projects. Then the attacker is going to publish this to a package manager, which at some point a developer is then going to utilize it, requires it as a dependency for their project and application, bring in that software, that untrusted code into the environment, and then have the ability to push into application, which is in production. So depending on the intent behind the attack, this is where we actually see the impact. Obviously, there's a lot of risks that come with this. Some of the very transparent ones are going to be code integrity, your infrastructure. When you have any kind of untrusted code running inside your environment, you have those obvious potential negative impacts. Depending on the type of attack, you also have the potential for operational or business impacts, which could, if it's customer facing, lead to credential and data exposure, all of which kind of culminate in compliance and regulatory risk that comes with it. But something I want to highlight is this reputational aspect. A lot of times us in cybersecurity are focused on the technical ideas, the technical things, how we can actually go about code, looking at it, identifying what's wrong. From a business level, reputational risk can be just as important, if not even more important, than an active notification for a breach. The idea here, and I'll bring in a real life example, is during kind of the early stages of the Russia-Ukraine conflict, there was a maintainer of a popular open source dependency who decided to use this dependency as a platform to preach their political beliefs. And so what they did is they had their dependency, they published a new version, and in this version, the code would check to see if the system that is running the application has a Russian IP address, and if it did, it would start printing their political sentiments to the screen. It didn't impact the actual application itself. There's no code integrity loss, there's no credential, there's no actual malicious intent behind it other than simply using it as a platform. However, businesses reacted in the same way as you would see an active attacker inside the environment, because this can be seen as a large company taking a political stance on a very charged topic, which can bring just as much negative impact as any other kind of breach would. So it's very important for us as cybersecurity to understand kind of the business level risk and be able to use that as an explanation for implementing different security controls. Now, let's actually take a look and see how this looks like in action. So, what I've done here is I went ahead and created a public NPM dependency. You can all look at this online right now. It took me maybe 15 minutes between creating the account and learning how to do this for the very first time to publish. I have two different versions. We have version 1.1 here, and then there's another version 2. Again, I cannot stress how easy it was to do this. There's no requirements necessary. You can put whatever you want on here. From here, I also made an application in Node in which it has the dependency of Hackmiami version 1. And all we're going to do is in this code simply require our package. It's the same kind of idea as like importing a Python package at the top of your environment. We're not actually utilizing any code. We're not actually creating any functions. Nothing is technically supposed to be executed. But simply by importing it, you'll see the code itself can be run. And all that's going to be happening, if we look at the code itself, is it should just print to the console, welcome to Hackmiami. So this is going through the idea of how you would normally integrate a dependency. If we do npm install Hackmiami, it's going to look on the internet, it's going to grab it, and then if we list, we can see we now have Hackmiami version 1 installed. So if we then just run our application, ignore the kind of warning at the bottom, but it prints to the screen, welcome to Hackmiami. Again, no actual functions are being utilized. All I'm doing is just ingesting the dependency into my application. But now what's to happen is if my next version, I as the maintainer, maybe my account gets taken over by someone else, maybe I just decide to go rogue, make an update, version 2. Same package, just the next version. We now have some different code. Instead, I'm going to print to the screen, you've been hacked, and then going to arbitrarily create a file and print something to it. For the example here, that's all I'm doing. You can obviously do anything you would want or anything you can do in JavaScript can be utilized. So if now in our application, we're just going to say that require version 2 now with the new update, we're going to reinstall our package. And then if we show, we now have version 2 installed. So all we're going to do is just again run our application. The only thing that we changed is the required dependency. And now we can see printed to the screen, you've been hacked. We look in our directory, we have our little crypto miner txt file, which if we print out arbitrary file creation, arbitrary text done. Again, anything that you can do in JavaScript can be utilized here and run as simple as that. So, kind of piggybacking off of that, another different attack, but very similar, is something called dependency confusion. The idea here is, what if the dependency that you're utilizing is an internal dependency, right? Something you maintain, something you trust, something you don't, in theory, have to worry about. Running through the same kind of intended mindset, we have our developer, they want to make an application, they're requiring a dependency, that dependency exists in the environment, so since it's all happening within the company intranet, in theory, we shouldn't have to worry about anything, goes back to our application, gets pushed to production, potentially as client-facing, depending on what the application is. However, in an organization, it is hard to differentiate the type of package and where the intended source of it is, whether it is from inside the internet or whether it's inside your company network or outside. So what many package managers do is they have logic that indicates, hey, go check both the internal and external repositories and pull out and just simply pull whatever dependency is required or whatever matches the name of the dependency that I'm providing. So the idea here is, what happens if a dependency of the exact same name is on the external repository that is additionally being checked for? If there's a name collision and there's two different packages, the logic behind most package managers, which is contradictory to much of their actual documentation, is let's look at the version, whichever has the highest version, return that. So if you have an external dependency with an arbitrarily high version number, and inside we're following normal versioning standards, the package manager is going to think, hey, you want the most up-to-date version, we're going to give whichever higher number it is and give it back to you. And then, of course, from the attacker mindset, what happens if it's an attacker who's the one who created this? So, running through the chain again, we're going to assume that there's an internal dependency that exists, protected, we trust, we maintain. An attacker is going to find out that we use an internal dependency by that name. A lot of different ways this can happen. Sometimes there's comments in code, sometimes it's on public GitHub repositories, sometimes you decompile code and it's in comments. Many different ways that you can do this, but the idea is someone creates an arbitrary, the same name dependency, but on the external repository, then pushes it to the package manager, and now we have our developer who's going to be using their internal dependency. They're going to make a reach out to the package manager. Package manager is going to look internal, external, name collision, return the one with the highest version number. Now it's in the environment. We're stuck with the same problem we just had. We now have external untrusted source code in our environment that's able to run inside the network on our applications, potentially customer facing. And I want to reiterate, and there's an amazing article on Medium about dependency confusion that kind of is initially kind of how it became known to the public. Highly recommend checking it out. It goes into a lot more detail than I can. But the big takeaway is that when you have a package manager that is looking for two different sources, even if you specify that you have a preference on one over the other and use the intended commands to say, hey, check here first, and in documentation it says that we're only going to check here if there's something there, we're going to ignore the second one. It doesn't actually operate that way. It will instead check the first location, regardless of if there's something found or not, check the second one, pull up whatever matches those names. If it's only one, just going to return whatever's there. If there's two, return the one with the highest version number. So let's take a look at how that looks. So similarly, I went ahead and published to PyPy another Hackmiami dependency with an arbitrarily high version number. Inside our application, we're going to have another dependency with the same name that this, as before, is just going to try to print welcome to Hackmiami. We then going to have our Python application that is going to simply just going to be running our dependency. And so working through as we would normally be intending to do this, what we're going to do here is we are going to create a HTTP server internal that's going to imitate our internal package manager. So all it's doing is just having an HTTP server, which is where our internal dependency is hosted. Over here in our environment, we're going to show that we have a few different dependencies already installed for the purposes of this demo, but Hackmiami is not one of them. So as we would normally do this, we would go and we would run something along the lines of this command, where we are trying to install the dependency Hackmiami. This is just saying, look at the actual link that I'm providing, not anything in the cache. And then here, we're indicating, hey, just look at our internal repository. Our internal package manager is where you should be getting this. If we run it, it's going to look at everything. And if we take a look here, the intended package is going to be downloaded, right? Our lower version number. And if we just go into Python, and again, we just import the package that we already have installed, it's going to run that code. Again, same kind of concept. We're not actually utilizing any code. We're just simply ingesting a dependency. One second. Now, move this over a little bit so it's easier to see. Now, we're going to clear our environment, kind of reset it back to square zero, uninstall any packages that we have, reinstall the requirements for the demo, and if we look again, Hackmiami is no longer there. The dependency is not present. Something that package managers will do is use logic similar to this command. Same as before, we're installing a Hackmiami dependency. We're not looking in our cache. We have index URL to indicate our internal package manager, what we just did. Then we have a different flag, extra index URL. If you look at the documentation, this is how you are supposed to do it if you have a secondary resource that you only want to check if the first one does not have what you're looking for. That is how it says it's supposed to operate. And it's just looking to pypy.org where the open source dependency is. If we run this and we look, the external dependency was installed even though we said we want the internal one focused in index URL. And if we go and again just import this package, we get printed to the screen, you've been hacked, arbitrary file download complete. So for this package, we made it a little extra fun. Similar to before, we create we create a text file, arbitrary file, right? I also had a URL that will go and download. In this case, it's not actually vulnerable, but the idea, it gets across, right? We can download anything we want. We can run anything we want, all from the perspective of how you would, anything that you can do with Python. And we can see we have our cryptominer.txt file and our totally not evil file. So, this is kind of scary, right? There's a lot of different issues that can come from this. And what can we as security individuals do? So there's a lot of obvious things that can be done in relation to preventing internal malicious code from being executed inside a network. Those are separate kind of security controls that are going to be independent based on different companies. Here we want to focus on how can we prevent these malicious dependencies from being ingested into our environment in the first place. First step is versioning. Versioning, listing out versions and making sure we're staying up to date both for our internal applications as well as the different dependencies that are being utilized. So think if we have an application, we're going to say it's on version 1. In our application version 1, we see that dependency version 1 is being used. But next time we update our application to version 2, the dependency version is now 9,999. That's something we can check for. We want to be able to see and understand the different versions that were being utilized. Updating, similar thing. We want to make sure that we're regularly updating our projects and our dependencies that we're utilizing within those. There's different mindsets into how frequent this should be, if there should be a delay, but the idea is we want to make sure that we are updating it at some point. We've seen many instances of different companies that are utilizing packages, known vulnerable packages for many, many years, and they just never touched it, never tried to update it. So being aware of what's in your environment and making sure you're updating is essential. Namespacing, when we have those name collisions for dependency confusion attacks, we want to make sure that if there is 2 different packages, we have the ability to differentiate between them. But if we prevent that at all, and at the very beginning, we as a company go to pypy.org and make an empty blank dependency of the same name as our internal one, no one else can do that. We can essentially prevent anyone else from creating something that we know we already utilize and kind of stopping this kind of activity from even being possible. Going on a zero trust idea, you could also have the ability to just create everything internal. That's very resource intensive, but it is an option and something that some companies will utilize, or for known special and intense applications or that are very important, specifically create internal packages just for the usage within those applications. Bug bounty program is amazing. T-Mobile has a great opportunity. Please check us out to learn more about it. But essentially, the idea is there's a whole lot of things that are happening, and there are researchers that are already doing this that don't work for your organization. So utilizing their assistance in allowing them to test your environment that they're already going to be testing and rewarding them and incentivizing them for doing so allows you to identify many different security risks that you otherwise wouldn't have been aware of. Research teams, whether this is having something internal to your organization or working with the many, many different third-party research teams, simply staying up to date. These types of attacks happen fast. And so being aware of when they're happening, that they're happening, and being able to respond quickly is essential. And of course, as always, there are many different vendors that are able to outsource this work to if it is something that you don't have the resources or time in order to do. Many different options for all different types of businesses. But the two biggest takeaways that you can have, the two biggest kind of assistances for preventing this is having an SCA program and creating SBOMs. SCA program, software composition analysis, is a process to identify and manage open source and third-party components. The idea here is you're looking through, you're trying to find vulnerable dependencies. Sometimes you can also work with legal to identify licensing issues, any kind of poor hygiene that's being utilized in the dependencies that exist within your environment, simply being aware of what's there and managing it. One of the common outputs for an SCA program is an actual SBOM, which is the software bill of materials. Think of this as just a giant list of, in this application, we have all these different dependencies of dependencies, which are called transitive dependencies. Anything that your code relies on in order to operate, it says what it's there, its version that's being utilized, when it's been utilized, how long it's been there, and something that you can use to understand what's in your environment and build tools around to ensure that you're understanding how long it's been there. Because ultimately, the biggest idea or the biggest kind of takeaway is that if something like, or rather when something like this happens, the best thing you can do is be aware of what's in your environment. If your security controls fails and there is something there, you want to be able to identify, okay, are we using this package? Are we using specifically the vulnerable version? Do we know which applications are using it? If so, how long have they been using it? All this information is essential in order to mitigate the potential damage, and these are the types of solutions that you can have for it. There are other solutions, not all of them need to be here. SBOM is great because it's often it's a very common and resource that is going to be introduced and have the ability to integrate with other existing tool sets, but there's many different solutions. But knowing what's in your environment is kind of key. But that's what we have. So thank you all for joining. I know we're running. Thank you. I know we're kind of running a little bit behind on time in general, so if you have any questions, feel free to reach out, come say hi to us. But that's all we have for you. Thank you.